So yeah, good morning everyone. I'll take you through to coffee break. So the sort of agenda for this talk today is a little bit about sample point discussion. I think I can quickly cover classification and monitoring because it's just been covered so well by Haseem. Then kind of getting into the risk assessments, and when I kind of got asked to do this talk, and I kind of looked where I was on the agenda, and we've had some of the other talks, and it was to kind of try and wrap it up and follow on from, you know, some of the discussions on Morgan yesterday on airflow visualization, Haseem, and you know, we know how we should be doing it, but kind of look into some of the where we're doing it and what that risk is and how we go through that process. Again, some of the design of the key components and some more kind of installation examples. And then just a kind of brief look at the data as well and some of the reports and trending data that we get and what to do with that data. So just starting off with a brief introduction of myself. I'm the sales manager for the UK and Ireland for particle measuring systems. My background is I'm a science graduate from UMIS, which was the University of Manchester Institute of Science and Technology. A lot of kind of capital sales experience, and then the last 15 years in the clean room and contamination control industries. A lot of experience in clean room testing, and I've presented training courses on particle counting and filter testing. So that's the work me. The real me. I'm a Ramsbottom United fan, but don't ask me about that this season. I like to watch the F1 as well. I've recently been adopted by a dog, so I get out and walk quite a little bit. And my latest kind of, I'm 55, it's probably past a midlife crisis, just crisis, is I've decided to volunteer as a special constable with the Lancashire Police. So I'm sucking the evil out of Burnley. You talked about sucking the evil out of clean rooms, so I'm trying to do it in Burnley as well. And I'm also known as that particle guy. I tend to ramble on LinkedIn occasionally as that particle guy. So first of all, just touching on classification and where we classify it. And this is all about establishing control, and it's checking that the cleanliness of the clean room is specified for the occupant's estate. So, you know, clean room classification, I think that was one of the quiz questions. Part 1 of ISO 14644 is about classification. And typically, sample points are located equidistant, at work heights, kind of a lot of formula tables. Some of these tables, we've got some classification cards out on the stand if you want to grab one. You know, this is the ISO. Again, as Haseem says, ISO is something that applies to clean rooms in any industry. And then we've all seen the GMP. This is, again, the section 4 of Annex 1, which is particle limits for classification. So that's where we don't have the 5 micron numbers for grades A and B. But then there's the other table in section 9 of Annex 1 for monitoring, which is what we'll kind of move on later. So all of the classification is again, about establishing the control, the sample locations. Again, there's a table within the ISO 14644. Depending on how big the room is, it tells us the minimum number of sample locations. There are formulas in there to calculate the sample volume as well, or the particle counters will kind of help you and guide you through that process, but that's in there, and calculations for the maximum concentration and a ratio of different particle sizes. So it's kind of all tables, formula, procedures, methods, but all very prescribed, kind of black and white, what we need to do to classify a clean room. So really what I want to move on to talk about today is more of the monitoring aspects of a clean room. And this is now coming back to, you know, selecting locations based on risk. So we're getting away from the formulas, we're getting away from the standards, and we're talking about risk. And it's the location of sample points to help us determine changes in trends in data. You know, a lot of this is understanding how our clean room normally operates, and then to sort of trend that and see what the changes are. So Data is obtained to understand variation over time and understand what's happening in the clean room and why that might change. And it helps us to sort of identify potential contamination events and trends. And, a time plot here, we've kind of set a limit of 100. We've got a couple of spikes here. That may or may not be an issue. Here, we've kind of got not as much of a spike, but it's for a slightly longer period of time. And then again, as we go along, we've got a very low level here, suddenly it shoots up. We're still well below our limit, so is that okay? You could argue yes. We could also say, well, now we're around 4 times what we were, so something's clearly changed and something has maybe gone wrong in the clean room. So even though you're below the limit, there's a significant change there, and I think most of us would want to know what's caused that and where that's from. So again, I think most of the papers I've seen have had a little bit of Annex 1 in there, and I'll be no different. But risk assessments performed in order to establish a comprehensive monitoring program, looking at locations, frequency monitoring methods. And the risk assessments are based on the process, facility and equipment, the actual operations within the facility, historic data. So some of this and some of this process is kind of checking, reassessing existing facilities and taking that data. But then, of course, we have to build new facilities, and sometimes we've got to look at, apply some of these processes to new facilities as well. Because we've already classified it, that gives us some data that we can then use as part of this monitoring risk assessment process. And again, with the microbiologist, knowledge of the typical microbiological impacts in that clean room and what might be affecting it. And it is something that should be reviewed regularly, so even though you may be doing it initially for a new facility, once that facility is up and running, or if you've already got an existing facility, it's about doing it. So some of the key things on here are the sampling locations, and we'll talk about that, the frequency of monitoring and the monitoring methods and the appropriate technologies there as well. So what do we review in these risk assessments? Generally, and the sort of starting point for this, to look at the sort of facility and the process as a whole, and look at a description of the production process and sort of try to understand maybe a flow chart of the process to understand what's being carried out where, by who. We look at the products that are in there. Is it liquids, powders, freeze-dried products? What are the clean room gates? How are we gowning to go into those clean rooms? We look at what the sort of current agar plate incubation conditions are, the strategies for the microbiological sampling. What media? Do we use any additives on the media? What isolates or microorganisms have been seen, are present, are expected. And then we look at the production. Again, some of these are continuous processes. Some are sort of a Monday to Friday, 9 to 5 process. Some it's just an hour or two for a batch. Some are, lines that are used for or an isolator or a safety cabinet that might be a week or two, different stages of the process. So kind of getting an understanding of that so we can assess the risk throughout the whole process. Kind of look at an abstract of the current environmental monitoring data, summarise what's there and what's been happening. And then particularly, for new sites, if it's a company with existing sites, can we draw on experience from similar lines, similar processes, or, our own individual experiences? A lot of us move around the industry, so what can we learn from our own experience of similar processes? Looking at the rooms themselves, we want to know the square metre area of each room, or, sometimes it's a room, sometimes it's a space or a zone, separate areas for filling lines, microbiological safety cabinets or isolators inside the room. What's the equipment in the room? Is there any clean room furniture in there? Looking at the room, what's the air? We can look up and try to look at where the air is perhaps coming in, exhaust grids. Again, why we want airflow visualization. If we've got that helps us understand the airflow movement within the room, and then kind of look at the people and the materials flow within there as we go about different activities. Layout of current sample positions and environmental classification protocols. For filling machines themselves, again, airflow visualization studies are very useful to help us with this risk assessment. Observing the production activities in the critical areas, what the operators, where they are, what they're doing, photos, diagrams of filling lines, safety cabinets or isolators, dimensions as well, any current sampling and you know what we put in initially, but again this is a constantly reviewed process, so what's in there now, and again this brief description of the production processes. So we work with clients, some people do it themselves, some people work with kind of consultants, but a typical team that we put together is we kind of have an advisory services team, so someone would sort of project manage that, but drawing on the experience of our product managers, our FMS team, our other advisory team members. I think with any organisation, you know, we have a depth of knowledge and lots of different people have different knowledge and things to contribute. And then sort of on the right-hand side there, the customer side of things, maybe led by their quality assurance team, but quality control, production, engineering, and other functions. Again, it's about getting everybody's input into this and agreeing things at the start so it's covered. So first of all, looking at the process and, you know, getting an understanding of the process, you know, looking at a facility, looking at where movement is. We've perhaps got some kind of safety cabinet or isolator here, a table here. We've got our in and out with step over benches in the middle. We can look at movement. There's some kind of storage tanks here. All just a simplified example, and I've kind of used some different examples from different assessments, so all this won't necessarily follow exactly one to the next as I talk about this, but starting to get that process understanding first of all. And then what we kind of do is, you know, divide this into what we'll call some functional areas. And you know, what you'll see is not every bit of the room is an area, and all these areas are different shapes and sizes. It's not, again, it's getting away from this classification where it's very formulaic, but we're looking at an area, and you know, just an example here, coming into the room, we're coming in and gowning step over bench, and you know, that's maybe more critical, so we'll perhaps have that as two different functional areas. When we exit and we're degowning, maybe we'll just take that as one functional area. Not necessarily the case for every application, but just showing some of the principles of, you know, the first step is sort of identifying these functional areas and trying to kind of guide yourselves through the process to do this in a logical way and to address all the different areas within a facility. Moving on then to a HACCP, a hazard analysis for critical control point review. So here, just again looking at some functional areas, what's the activity within the area, the personnel and materials in transit, or some equipment, a weigh table in an area. You know, are materials or equipment exposed to the environment? Could personnel contaminate the product? Is there another close by critical control point? And then do we make this a critical control point or not? And it's looking at all those functional areas and kind of going through it once, then stepping back, looking through again to see how they all fit together. So that's the first stage of the critical control points. And then to start to sort of map the area, so we'll say, yeah, looks like we might need some in this area maybe not, down here we need some, and kind of just identifying some of those different areas of the facility and to where those critical contamination control points might be. We then get into some sort of risk assessment, and again it's things like, you know, is product stored here, is it in transit through this area, how long is it in this area, how many people are in the area, we can identify weightings for many different parameters, and without going into the detail of that, but we typically kind of run a risk assessment process and then, you know, calculate a number. You'd give different parameters a weighting, multiply them all up, and we'll get different numbers. Again, depending on how many parameters we're looking at, the scales vary from kind of assessment to assessment. But, you know, we might say in this example, over 400, maximum number was 960, but over 400 is a kind of higher unacceptable risk, a medium kind of mid-level risk, low as reasonably possible, and an acceptable. So looking at each sort of functional area and doing this sort of calculating this risk priority number to then really start to help us focus on what to do. So out of that, within these CCP areas, critical control points, we start to build up, you know, where we might want to look at potential sampling point locations. And again, this is the sort of first stage of it. You know, within that area, there's lots of possible points. But you'll see some are nearer to equipment or some are nearer to walls, some are in the middle of nowhere. And it coming back to, again, some of the examples before about practicality of locating the points. Again, we can go back to our risk assessment and kind of, you know, get into individual points within a functional area and look at the higher scoring ones. And, you know, that, again, where we're getting the high scores, that's where we'd most likely want to put a sampling point if we can do so. So that would be the ideal situation there. So from that, you know, we start to narrow it down, and we might have, you know, identify points where we take viable surface samples, non-viable total particulate points, and then the active viable sampling and passive viable locations for our settle plates. So again, depending on the equipment there and the practicalities, where do we put the sampling locations? But that would be that sort of definition of the locations. Again, touching on, keep coming back to the risk assessment, but looking at whether they're sort of in the green, the amber or the red zone also guides us on frequency. Going back to the Annex 1, one of the things talks about the frequency of sampling. So we've got to assess each point and each test, but there may be areas which part of a continuous facility environmental monitoring system. You know, there might be some areas we say we'll just do every couple of weeks, something every batch, something at the end of every shift. So lots of different sort of sample types and sample methods, and we've got to assign frequencies to those. Some of it, again, is sort of mandated by documents like Annex 1, but some of it is all part of that contamination control strategy and our risk assessment. We've got to evaluate the different sampling methods that we apply. So there are the more traditional methods, so surface sampling, but do we use a contact plate or do we use a swab? It might be, you know, the type of surface that we're trying to measure might dictate whether a swab or a contact plate is more appropriate, or the access to that surface. Viable and non-viable monitoring systems. So, you know, plate handling. I think Mike in his talk this morning talked about access and getting into to move these plates and to fit the plates, and that absolutely is an issue. Do we use remote particle counters or do we use portable equipment? Flow rate for non-viables as well. Usually it's 1 CFM if it's a continuous monitoring system. But again, if it's portables, there may be applications where we can use the 100 litres a minute rather than the 28 litres a minute 1 CFM units. We've got to look at the applicability of the real-time methods that we heard about earlier, and you know, alternative methods. That's something that's coming in. Rapid methods as well, I guess it's the terminology, but that there are, I think Mike again covered that Annex 1 is kind of encouraging that approach and something to be considered. And then, you know, with the viable active air, single-use technologies, this is, you know, something we have where we've got customers, not in every case, but we've got some customers now pushing towards 4 hours of continuous active air sampling. So we're getting away from that bookending approach. And again, I think Mike mentioned, you know, there are changes there that allow us to do that with the slip method and some of the media and the fill we've got. So moving towards longer sampling is something that you can consider. You know, an advantage of that is, again, that allows us to sort of do the isolate investigations, which was discussed earlier and is something that is a requirement. So there are ideals as to where the sample points should go. We've got to look at the physical installation of the sample probe. And again, a lot of this is kind of touching on some of the things Haseem talked about in the technical report 21. Physical installation of the instrument, so the size of the instrument, you know, particularly when we're on filling lines, there's a lot of equipment in that technical area underneath the fill line, and everybody's fighting for space for their equipment, and we want to get this in the right position, and that helps us with the tubing length and the number of bends and things like that as well, which, as I say, I'm not going to go into a lot of detail now because that was well covered by Haseem. And, you know, the number of sample points, it's usually less than the sort of ISO 16444 classification norms. That was all based, as showed the table, it was based on the area of the facility. But there's no formula here. It's all coming back to this risk assessment process. So a few examples into, you know, one side, often slightly above the critical location, and I think this is the FDA guidance that you mentioned as well, this 1 foot or the 30 centimetres. Just above the critical point, you know, then you're kind of seeing what the critical point is but you're also kind of minimising the chances of getting in the way of the operators or contaminating it, and you know, contamination from the process, anything that might get spilled and go down and into the particle counter may even, you know, we have particle counters that have been filled with product on occasion, best avoided. Not too close to the filters, you know, we don't want to just prove we've got a little area of filter is working, so not too low, not too high, and not too close to the process to sort of get in the way or risk contamination of the sensors as well. And ideally not directly over the point, you know, that can create turbulence and starve the process of that clean air as well. So a couple of examples there. That's the isokinetic for the non-viable sampling. Typically it'd be a bit higher up, and there's the a viable sampling collection head that'd have the plate inside there. And then again an overview of that at the sort of side of a line there next to some vials slightly above it, or the single-use technology there that can be sort of replace that with a slightly different style bracket. That's also kind of, we're seeing more of that as we come into some of the sort of robotics and reducing interventions. Those are kind of a lightweight plastic one that can be placed by robotics. Filling lines, again, depending on the size of the line, there's no one size fits all, but typically 3 locations. And for those with circle, one at the back there, another isokinetic there, and a larger one at the front. It's not always easy to see these on some of the photographs. And then maybe a capping point and lyophilization areas as well. That's another active air. Background areas, again, kind of Annex 1 and wants to encourage continuous monitoring in the grade A and B areas, but sometimes if you're putting a system in, some of the background areas may be a B, but even other areas, it's just reducing someone having to walk around with the portable, so you know, there's often kind of continuous monitoring of some of the background areas. You know, that's directly mounted to a wall. And again, this is again a big kind of thing of we need to get services. Some just, you know, need a single cable for power and data, and that can have a built-in pump. Sometimes we need vacuum tubing to it. You know, we may need power, vacuum tubing, and data connections to a particle counter. So depending on what you're using, that has some bearing on locations, but that's an example directly mounted to a wall, and again going directly into it. Here, you know, the facility allowed it to be a flush mounted one with it mounted inside a wall enclosure. And this was an example where we've got the isokinetic tube and a sort of radius bend inside the room, but then the actual counter is on the other side of a wall. So lots of different kind of examples depending on the design of the facility and the practicalities of doing it. Some of the kind of newer technologies in ATMPs and cell and gene therapy products, some of this work's kind of done more in microbiological safety cabinets or isolators. Typically sort of one non-viable, one viable microbial sensor. If it's a sort of bigger system, maybe a 4-glove isolator, might be 2 filter banks, so you could maybe look at 2. And again, is it 1 work zone or 2 work zones? How many operators are in there? Sensors sort of mounted below or on the side of the cabinet, and kind of like some of the sketches in the 21 document that gave some ideas there. And kind of plumbing things, that's probably a slightly tighter radius than you might want. Sometimes in these, again, processes can take a number of days, and it's different processes on different days. So, you know, this is the viable sampling thing, and I think that looks to be on a flexible tube. And the one argument is you can kind of move it closer to a particular process. The kind of converse of that is it gets moved away to the far corner out of the way. So, but we see more kind of CCTV systems on some of these in some of these facilities. So it's about, you know, your SOPs and maybe the CCTV to keep an eye on it as well. But, you know, accepting that it's not always a one-size-fits-all, and what's good on one day might not be the best location for the next day if you are doing kind of different processes on different days. And kind of pulling it all together into, you know, the continuous part of the system, you know, where we've got viable, non-viable sensors with and without pumps. We've got the stainless steel heads, the single-use heads, there's real-time monitors, and then we can kind of have portables in there as well, and maybe the environmental. So just kind of pulling everything together into a larger system, and all of that is going to create lots of data. So again, going back to how we started, it's about looking at the data, and, you know, first of all, really understanding the performance of our system, you know, what the data is, what's normal for our system, and looking at those trends so we can review them periodically. It's looking at revision of alert and alarm levels based on that evidence that we have. So, you know, perhaps new facilities tend to set higher alarm limits and then drop it down once we get the confidence in the facility. You know, use of pre-configured alarm acknowledgement, so that helps trending. You know, if we allowed free text, I'm going to type in cleaning. Morgan, from his talk yesterday, is going to type in spray and pray. But, you know, if we're all got a drop down and it's, you know, prescribed text, then that helps us trend the alarm causes where we know it. You know, consider what we call N of M triggers. So maybe if it's a single sort of excursion for one, you know, typically we get 1 minute of data. You know, maybe that's less of an issue than if we get 3 in any 5-minute period or 2 in any 3-minute period, something like that. So that kind of approach can be used. Consecutive reading. So again, you know, and it went back to, we report the data as particles per cubic minute, but that's this 35-minute rolling data to really take quick action. I like to look at that 1 minute data as well. But maybe if it's 5 consecutive minutes is when we look at actions. And allow for any tubing losses in the setting of action levels. And again, I think that was the same said. So, you know, if we were at 100, but we've identified tubing losses, maybe we need to drop that down, and our limit is 80 to take into account those tubing losses. So that was something there as well. So, yeah, thanks to the Cleanroom team, the AV guys at the back, the speakers and exhibitors, and Steve and Tim yesterday for chairing the sessions. One of my colleagues in the US has kind of helped me with this presentation, so I just wanted to acknowledge the input from my colleague Mark Horworth, and for you guys for not leaving. Thank you. Any questions?
That was great, Andy. Thank you very much.
Thanks.
Got time for a couple of questions? Straight away, look at that. Thank you, Warren.
Thank you. This is a question, Andy and Hasim, you might want to jump in here. One of the issues or concerns I always have, at least in life science, when people will monitor like a cabinet, they'll set up an isokinetic probe for continuous monitoring of a BSC or a flow hood, and the probes are always facing upwards towards the HEPA filter for monitoring. And back in my lifespan when I worked in electronics, we would never do that. We would always have the probe facing towards the risk, right? Because we wanted to monitor where the contamination was coming. This is part of process monitoring. And in life sciences, everyone doesn't want to do that. They always want to have the continuous monitoring probe facing upwards of the HEPA filter. The HEPA filter is not ever the risk, unless, of course, the unit's off or the filter fails, which really shouldn't happen. And the times we place the probes facing towards the risk, we've gotten hit on it, so no one does that. I just wonder what your thoughts are on that.
I must admit, it's not really, I think it's a really interesting point. It's not something I think I've ever really come across or heard that comment. I think it makes a lot of sense. I would certainly say, you know, and I think I touched on it, a probe height, if you are pointing upwards, you know, it shouldn't be close to the HEPA, because all you're really doing is just scanning a small area of HEPA filter. But yeah, I think there's an argument there
it's just
to do it. I can't say I've seen it done, but I kind of certainly can see where you're coming from. And
I think CETA in the US come up with a very good document to identify this point. They said that in the primary engineering units like biosafety cabinets or laminar airflow workbench, they said that, okay, the practitioner's area for their term within their hands, that's the risk zone. Whatever you do, we will be considering this location as a risk zone. So we will be still within 30 centimeters away from this area, but nearby. But facing upwards still should be continue, because there's no difference between the production line, HEPA filters on top, and the risk point down, and we are facing upward based on the ISO. And still, I consider having it upward, but not sampling directly from the HEPA filter, because in many applications, we are either very close to the HEPA to see and verify is like a particle checker. We're not expecting anything to come from the HEPA filter because it's already tested. But we are expecting it to be nearby the risk location, which is a direct integration area where the operator do the process. So it will be closed, but still facing upwards to the HEPA filter if it's a laminar flow.
Yeah, and adding to that, isokinetic sampling again, where if we start to point away from the unidirectional flow, we struggle with the lack of isokinetic sampling, and therefore we don't quite sample the right particles we're looking to see. So.
We don't really want to collect particles through the process by sucking them. We really want to see all particles dispersing around so that the operation is not safe anymore. Instead, if we will go directly to the operator's activity and try to suck air, then we will start sampling the process itself and the particles that are generated through the process. In fact, we don't want to see any other activities around it to consider it as a safe to continue.
Yeah, that's much different than in electronics, where when we would use particle counters as part of real process control, and we wanted to see the particles from the operation, and we weren't monitoring for the isocleanliness, where I'm monitoring to understand what the particles were, and we'd use those numbers to control our process. So it's a bit different approach.
Okay, thank you.
Was some of that even using horizontal laminar flow, so you were actually facing directly opposite the direction of flow, potentially, or?
Another quick question, did you?
Well, I was just going to expand on the difference between sampling source versus
There you go, expand.
product protection.
Expand away.
I think it was just, I think Hasim was saying, it's you don't want to sample the source if the operation is generating the particles, it's not a risk to the operation per se. So you're trying to protect the open manipulations that are there. So if what I'm doing is generating some particles that but it's inherent and it's below. So for example, taking the top off something, it's still sealed and then moving away. I'm not worried that I've created those particles. I expect to create them. So I wouldn't be looking to actively pull from there. I want to make sure nothing drops into my product.
You're really monitoring for compliance, you're not monitoring for control.
Exactly.
Thank you, Chris. Any other questions? Oh, one from Gordon.
Thank you, Steve. Gordon Farkas, remember that in the GMPs now there's very common talk about first air. And the assumption is that we're interested in that air derived from the HEPA filter at a critical control point, and that we're demonstrating that there's nothing interspersed between that air source and the sensitive critical task. But we're always compromised, because ideally we'd like to put the isokinetic sample directly in line with the open container, but we can't do that. So we go as close as we can without disturbing that air flow. So it's a reasonable representation. And then the debate that we had before about the US FDA 1 foot rule, which I think largely people would say that's cheating. My words, not FDA's words. But we want to be better than that. But it's a judgment, isn't it? So we want to be as close as possible with our isokinetic sample. Our assumption in the life science sector is that the particles generated by the process are not a hazard to the product or the manufacturing. Because remember, we're using particles here. The semiconductor industry is actually worried about killer particles that land on the device that cause failure of a circuit, on a chip. We are not interested in submicron particles at all. There's no specification for submicron particles in parenteral products. We're using it as a surrogate. We're sampling the particles 0.5 and larger and 5 and greater, because it gives us an immediate indication of a contamination event. We're not interested in submicron particles. Our assumption is that sensing those particles could be an indicator of a microbial event. So it's very different, picking up Morgan's point, to microelectronics, where they can actually want to look at killer particles. I use that word, I think it's quite a nice phrase. But we're using it as a surrogate.
Thank you, Gordon.